Hello, I'm Wolfgang Schwert with RAS Engineering, and welcome to the economic sense of high-performance buildings.
RAS Engineering strives to test the performance of building elements used during construction to provide high-quality results, with the belief that testing and discovering energy-efficient solutions with fast payback is not only possible, but makes financial and economic sense.
Economic Sense of Backup Window Series, Episode 1, Air Infiltration.
The envelope of a building, which is the exterior surface of a building, is the shield protecting the occupants from the environment. In addition, elements like windows have a great impact on air conditioning performance and drastically affect the energy efficiency of a building. In this window testing series, we will prove that restoring your building with energy savings in mind makes a lot of economic sense. On the last episode of the series, we will evaluate the economic benefit of these tests, compiling all the testing results from the series.
This side of the mock-up simulates the exterior side of a wall on the building. On the interior view, notice that the top standard window is covered by the backup window. The backup window has several distinctive features. You can see how deep and solid the frame is. This window allows for high impact. This is valuable in the event of hurricane winds preventing breakage or blast explosion. Demonstrating with a hammer, the window does not break, but the glass in the standard window would. The window also has insulation inside on the frame. There is no contact in between the metal of the window with the exterior, meaning there is no thermal bridging that transmits the heat from outside into the metal, reducing transmission of heat, sound, infiltration of moisture, and pollutants.
Today we are running an air infiltration test, measuring and comparing air leaks in both a standard window and a backup window. We will then calculate the energy savings based on the difference of air convection and wasted cooling air.
Here we have the testing equipment set up on the windows. The blower is connected to the air chamber by flexible ductwork. The chamber is attached to the wall using the clamps for a tight seal. The green tube is a sensor that measures the differential pressure in between the environment and the interior air in the chamber. We will be using a blower to pressurize both windows one at a time. This is the interior side of the window. As you can see, the top window has the backup window installed, while the bottom window is just a standard window. We are setting the pressure gauge at 50 pascals to test the upper window with the backup window installed. This screen comes from the computer showing the results of the airflow and pressure. The program automatically calculates the annual cooling cost for this window. Now we will disassemble the chamber and reassemble it to pressurize the lower chamber covering the standard window below. We will set the pressure gauge for the same pressure we used on the upper chamber and turn it on. You can see again the ductwork is expanding as more airflow is passing through. The difference is an extra 300 CFM passing through the bottom window into the interior of the room. This airflow was blocked by the backup window on the first test. Here on the screen we see the results of the testing. The annual infiltration is almost 902 air changes per hour, and the estimated cost of air leakage is $37 per year in cooling alone for a small window of this size. And of course, the cost of wasted cooling air and energy will rise on windows of an even larger size.
Now, let's take a look at the building code. Maximum allowed air infiltration in buildings is ruled by the three major building codes: California, Florida, and New York. The maximum infiltration rate allowed in windows varies if it's a commercial or residential building. The maximum allowed air leakage rate through the envelope in residential buildings varies in California and New York, with the Florida, which is sustainable, higher. The maximum allowed air leakage through the envelope in commercial buildings was set by the codes at 0.04 CFM per square foot. And let's do the math.
We are now going to place the results of the test into a chart. The perimeter of the standard window is 86 inches, and the test concluded that the annual infiltration rate came out to be 37.6 cubic feet per minute. If we divide the infiltration rate by the perimeter, we find that there is about 0.44 CFM per inch of caulking. The cost of air leakage per year results in 43 cents per inch of caulking. Reviewing the annual infiltration rate from the backup window, the infiltration was only 4.5 cubic feet per minute, which in this case divided by 76, which is the perimeter of the caulking on this window, we reach 0.06 CFM per inch. The cost of air leakage per year in this case comes down to 5 cents per inch of caulking. Now we will use an example of backup windows installed in 3 rooms in Miami, Florida, with a size of 6 feet by 4 feet approximately. The caulking perimeter of the standard window would be 1,222 inches, and in the backup window, which has less caulking than the standard, it would be 720 inches. We are going to apply the calculated value of cost of air leakage from the first chart for each window, and assuming 10 cents per kilowatts hour, we will see an annual cost of $526 for the rooms with standard windows. In comparison, the rooms with the backup windows would only cost $36 per year. This gives us a savings of $490 per year on the infiltration of air for just 3 rooms. In this series, based on the benefits of the backup window, the savings so far amount to $490.
Thanks to Green Bee for letting us test the backup window. If you would be interested in backup windows for your building, check them out at www.greenbee.solutions. If you'd be interested in contacting RAS Engineering for any services for your building, please check us out at www.ras.engineering. Links in the description below. And please follow our YouTube channel for the latest state-of-the-art testing videos on new solutions to improve your building and turn it into a high-performance building. Thanks for watching.
To receive alerts about monthly episodes of research and development for high-performance buildings with economic sense, sign up at www.ras.engineering.